Welcome to the deep dive. This is where we take dense information, could be articles, research, sometimes really specialized technical stuff, and we pull out the most important, the most surprising, and, the really useful insights. Our goal is basically to give you that essential shortcut, help you get properly informed without drowning in details. Today, we're diving into the world of Cisco wireless networks. Now, before you think that sounds maybe a bit too niche, our main source material for this is actually built around a pretty high-stakes certification exam. It's the Cisco 300-430 wireless exam.
That's right. And, while the source is an exam, the practice questions, and especially the explanations that come with them, they're just a goldmine. It's actually an incredible shortcut, like you said, to understanding the real core challenges and some of the really clever solutions that make modern Wi-Fi networks tick. It's not just about making them work, but work smarter for all of us.
Exactly. So our mission for you today is to kind of distill that practical knowledge, find those aha moments. We want to turn these potentially dry technical details into insights you can relate to how these networks manage everything from, say, your video calls to tracking assets in a warehouse. And just for context on the exam itself, it's web-based, 90 minutes, maybe 55 to 65 questions. Passing score varies, but it's usually around 750 to 850 out of 1,000. Oh, and it's offered in English and Japanese. Okay, so let's unpack this. Let's dive into some specific scenarios we pulled out. All right, first up, imagine you're a network engineer. You've got this critical business application. Maybe it's real-time trading, maybe something medical. It just has to work perfectly, right? Even if the Wi-Fi is super busy. How do you make sure that app's traffic gets, priority, gets to the front of the line?
Yeah, that's a classic quality service QoS problem.
Yeah.
And the smart way to handle it on a Cisco wireless LAN controller, the WLC, involves two key steps. First, you've got to enable something called Application Visibility and Control, or AVC.
AVC, okay.
Right. This is what lets the WLC actually see and identify that specific business app's traffic. It's not just generic data anymore. Think of it like a smart filter. Second, once it can see the app, you configure a Layer 2 QoS policy. And this policy specifically matches the application's DSCP value that's differentiated services code point.
DSCP, like a priority tag.
Exactly. It's a little tag on the data packet saying, I important. So AVC identifies it, the QoS policy sees the tag, and boom, that traffic gets priority treatment on the wireless network.
Huh, that's interesting. So it's not just about tagging. The WLC has to actively recognize the app itself. I might have thought, maybe just assigning a default QoS profile or maybe a basic access control list, an ACL might work. Why isn't that enough?
Well, it seems simpler, right? But those generic profiles or ACLs, they just don't have that granular application-aware control you need. Without AVC, the WLC might see packets, but it can't really tell your crucial trading app apart from, say, someone streaming cat videos in the next cubicle. You need that intelligence to know which app it is. This really shows the power of combining wireless QoS and AVC.
Okay, so the takeaway for you listening is, when your video conference call isn't glitchy, or maybe that important work app feels really responsive, there's probably some intelligent QoS working behind the scenes. It's like a silent traffic cop making sure those important packets get the VIP lane. Okay, let's switch gears a bit. Let's talk troubleshooting. What happens when just one specific user, maybe it's your laptop, maybe it's a critical device like in a hospital, is just having a terrible time on the Wi-Fi? How does an admin get that really detailed, live view of what's happening with that specific connection? Association, authentication, getting an IP address, all of it.
For that level of detail, the go-to feature on the WLC is client debugging. It's incredibly powerful. It basically gives you a running real-time commentary of everything happening for that specific client's wireless session. It's absolutely vital when you're trying to track down those really tricky client-specific problems. I actually remember one time we were pulling our hair out over this one connection issue. Turned on client debugging, and bam, it showed the client's clock was off by 5 minutes, totally messing up the authentication handshake.
Wow. So instead of just guessing or asking the user a million questions,
Exactly.
you can actually see the step-by-step process and where it's failing. It's like having a microscope on that one connection.
Precisely. Looking at other things like the overall AP status page or the network summary dashboard, they only give you the big picture. They might say the AP is up or the network is generally healthy, but they won't tell you why this specific device is struggling. Client debugging gives you that per-client diagnostic view. That's client debugging and real-time monitoring in action.
So for you, if you're ever the person with the frustratingly slow Wi-Fi, this is the kind of tool the network pros use to figure out super quickly if the issue is actually your device, maybe the signal right where you are or something else entirely. Gets you sorted faster. Okay, here's something that often catches people off guard about wireless networks. It's a bit counterintuitive. Let's say an engineer is setting up a new multicast application. Could be a live video stream going out to, say, hundreds of employee devices at once. What's a really key but often surprising thing they need to consider for it to be delivered reliably over Wi-Fi?
Yeah, this is a great one. The core insight here is that, by default, multicast traffic on a wireless LAN on Wi-Fi is inherently unreliable.
Unreliable, really?
Yes, really. That surprises a lot of people. See, normal traffic, unicast, one-to-one. Every packet usually expects an acknowledgement back. Yep, got it.
Yeah.
Multicast, one-to-many, it's typically just sent out, fire and forget, no acknowledgements. Plus, it's often sent at the lowest possible data rate to try and reach everyone, even people with weak signals.
Lowest rate. Oh, wow.
Right. Which means, in a noisy Wi-Fi environment, the chance of losing packets goes way up.
That completely changes how I thought about multicast. I just figured it was efficient, sending one stream to many people. If it's unreliable by default on Wi-Fi, how do you actually make it work for something important like a company-wide video address?
Well, you hit on the efficiency part. It is efficient with bandwidth, but that comes at the cost of reliability on wireless, unless you configure it properly. So on the WLC, you need specific configurations. For instance, you might tell the WLC, okay, convert this multicast stream into individual unicast streams for each client. More bandwidth intensive, yes, but way more reliable because you get those acknowledgements. Or you enable specific reliable multicast features that add some of that checking back in. The key takeaway is that it's not automatic, it's not automatically reliable, it's not automatically converted, and it's usually not sent at the highest speed. Understanding this is crucial for wireless multicast behavior.
So if you've ever been on a group video call over Wi-Fi and it got really choppy, or maybe a live stream kept pausing, this inherent unreliability and the need for specific fixes might be exactly why. It really highlights how the wireless part adds unique wrinkles. Let's shift over to security for a moment. Imagine this. A security audit finds that a Cisco WLC, the controller, its CPU, is just getting hammered. It's running super high, almost maxed out, and the cause? A flood of management traffic, but it's coming from unauthorized devices. How do you protect the controller itself, the network's brain, essentially from getting swamped like that?
All right, that's a dangerous situation. You need to protect the control plane. The crucial feature here is control plane ACLs, or CPACLs. You configure these directly on the controller. These are access control lists, but they're special. They specifically filter the traffic trying to reach the WLC's management interfaces. They basically say, only these specific authorized devices are allowed to talk management to me. By doing that, you're directly shielding the control plane, the part handling all the critical commands, configuration decisions from being overwhelmed by junk traffic or even a potential denial of service attack.
Okay, so this is like a dedicated bodyguard just for the WLC's management functions. How is this different from other security stuff, like, say, radius authentication or 802.1x? Aren't those important too?
Oh, absolutely vital. Radius, TACAX++, 802, and 2.1x, they're crucial for verifying users and devices that want to access the network itself. But they don't necessarily stop a rogue device from just blasting the controller's management interface with packets. CPACLs are specifically designed to stop that kind of attack, malicious or excessive management traffic, aimed directly at overloading the controller's CPU. It's a fundamental aspect of control plane security.
So think of the WLC as the central command center for your Wi-Fi. CPACLs are the reinforced doors and security guards protecting that command center, making sure it stays operational and secure so your Wi-Fi keeps working reliably. Okay, let's think about network design, particularly for places like branch offices. An admin needs to set up a FlexConnect access point that's an AP that can work more independently in a remote office. They have two main requirements. First, contractors working at that site. Their traffic needs to be switched locally right there at the AP for speed. Second, all user authentication still has to go back to the central Radius server at the main office for security consistency. What two specific FlexConnect features make this kind of hybrid setup possible?
Right. This is a really common and useful scenario. You need two specific things enabled for that FlexConnect AP group. First is local switching. That's the feature that lets the AP handle the ADA traffic directly at the remote site. So if two people in the branch are sending files to each other, it doesn't have to go all the way back to headquarters and come back. Much faster.
Keeps it local. Makes sense.
Exactly. And second, you need central authentication. This ensures that even though the data traffic might stay local, the actual login requests, the username password checks, get sent back to that main Radius server. This way you maintain your corporate security policies, user profiles, everything centrally managed.
That is a pretty neat trick. You get the local speed, but you keep the central security control. seems really flexible. Why wouldn't other options work here? Like, could you do local authentication or maybe something called VLAN-based central switching?
Good question. Well, local authentication wouldn't work because the requirement was specifically for central authentication via radius. And VLAN-based central switching, while it is a Flex Connect mode, actually does the opposite of local switching. It sends the data traffic back to the WLC for switching. So it wouldn't meet the requirement for local traffic efficiency. This scenario really nails the specific use case for combining local switching with central authentication. It's all about understanding those different Flex Connect deployment modes.
So for you, this explains how big companies can manage Wi-Fi effectively in all their branch offices. They can keep things fast locally for the users there, but still make sure everyone is logging in securely according to the main office rules. It's distributed efficiency with centralized control. All right, let's move into some more modern applications. Think about a large retail store. They're using Cisco CMX, that's their Connected Mobile Experiences platform, to offer some cool guest services. What they want to do is send a targeted push notification, maybe a coupon or a welcome message, to a customer's phone right when they walk into a specific area, like the shoe department or maybe just the main entrance. Which part of the Cisco CMX system actually handles that kind of location-aware notification?
That capability comes from presence services within Cisco CMX. That's the specific component designed for this kind of location-based engagement. It allows the store to define zones on a map and then trigger actions like sending those push notifications or maybe changing digital signage when CMX detects a device entering or dwelling in that zone. It's how they make the physical space more interactive.
Presence services. Okay, that's fascinating. So it's not just about knowing where a phone is, but actively doing something based on that location in real time. Turns the store into a smart space.
Exactly.
Yeah.
CMX has other parts too, of course. Like detect and locate is more about the basic tracking, just seeing where devices are on a map. Analytics is for crunching all that location data to find trends. And connectors help integrate CMX with other systems. But for that direct zone-based engagement and push notification piece, that's powered by presence services. It's the core of CMX presence services.
So think about this. Have you ever walked into a store and almost instantly got a special offer ping on your phone related to where you were standing? Or maybe connected to their guest Wi-Fi and got a welcome message. That's this kind of tech in action, aiming to make your visit more engaging or maybe just smoother. Pretty neat stuff. Okay, let's tackle a really common challenge for companies these days. BYOD, bring your own device. The company wants things simple for users, so they use just one Wi-Fi network name, one SSID, for everyone, employees with company laptops, people connecting their personal phones, maybe even guests. And here's the key. They need to give these different users and devices different levels of access, maybe put them on different network segments, different VLANs, or apply different quality of service rules. How do they enforce these kinds of dynamic, context-aware policies with just that single SSID?
That's where Cisco Identity Services Engine, or EYES, becomes absolutely essential. EYES is the brain behind this kind of intelligent access control. It works hand in hand with the wireless LAN controllers. When a device connects, the WLC asks EYES, hey, who is this, what is this, and what should they be allowed to do?
Right.
EYES then looks at a whole bunch of things, who the user is based on their login, what type of device it is it corporate managed, is it a personal iPhone, maybe even checks if the device meets certain security requirements, like having antivirus updated. Based on all that context, EYES tells the WLC exactly what policy to apply, which VLAN to assign, what QoS level, which resources they can reach.
Wow. Okay, so EYES is like the ultimate network traffic director, sorting everyone out based on who they are and what they're using, all behind that one simple Wi-Fi name. That sounds incredibly powerful for managing complexity.
It really is. It gives you that flexibility for BYOD without sacrificing security or control. Simpler tools like DHCP snooping or even network management systems like Cisco Prime Infrastructure, they just don't operate at this level of dynamic, identity-driven policy enforcement. SNMP v3 is for management, not this kind of access control. ISC is the one making those granular decisions in real time for every single connection. It's the heart of identity-based access control.
So, if you connect your personal phone or laptop to your work Wi-Fi, this is the kind of sophisticated system working in the background. It's intelligently figuring out, okay, this is a personal device, maybe they only get internet access. Or, this is a corporate laptop logged in by an engineer, they get access to the servers. It keeps things secure, but also workable for everyone. Here's another really interesting, maybe even surprising use for your existing wireless gear. Let's say an organization wants to use Cisco CMX again, but this time their goal is to track physical assets, maybe valuable equipment in a hospital, or inventory pallets in a warehouse. They're using RFID tags on these assets. What device that's likely already part of their Wi-Fi infrastructure is needed to actually pick up the signals from these RFID tags and send that location info back to the CMX server?
Okay, this one might genuinely surprise you. The answer is often the standard Cisco access points themselves.
The Wi-Fi APs? Really? They can read RFID?
Many of them can, yes. Either they have RFID readers built in, or they have ports where you can connect an external RFID sensor module. So these APs that are already providing Wi-Fi coverage can simultaneously listen for signals from nearby RFID tags. When they hear a tag, they report that information, along with signal strength data, back to the CMX server. CMX then uses data from multiple APs to calculate the tag's location.
That's incredibly efficient. So you don't necessarily need a whole separate network of dedicated RFID readers.
Exactly. In many cases, you can leverage the investment you've already made in your Cisco wireless infrastructure to add asset tracking capabilities. It's important to note, though, that other network devices like switches or routers, they can't do this. They don't have the radios to pick up RFID signals. It's the APs that do the listening. This capability falls under the umbrella of wireless asset tracking.
So for you, think about large spaces like warehouses, hospitals, universities, even big retail stores. The Wi-Fi network isn't just giving you internet, it could also be silently keeping track of thousands of items, from medical pumps to shopping carts to forklift trucks, all using the same APs. It's Wi-Fi pulling double duty. Okay, let's circle back to Flex Connect one more time. We talked about local switching earlier, but what about the other main mode, VLAN-based central switching? In a big company network, what's the key benefit of using this mode? How does it actually simplify the overall network design?
Right, VLAN-based central switching. The core benefit here, and it might sound a little backwards at first, is that it simplifies network design by allowing the WLC to control all the traffic switching, even for APs at remote sites. Instead of having to configure potentially complex VLANs and subnets at each individual branch office location to support the wireless users there, you essentially tunnel all the client traffic from the FlexConnect APs back to the central WLC. The WLC then handles putting the traffic onto the correct VLAN based on the SSID or user policies. So the configuration complexity stays centralized at the WLC rather than being distributed out to every single remote site switch.
Ah, I see. So even though the traffic travels back centrally, which might add some latency, the management and configuration become much simpler because you're handling the VLAN assignments in one place.
Precisely. You centralize the control logic. It makes deploying APs in new branches much easier. You don't need a highly skilled network engineer on site configuring complex switch settings just for the wireless. It's crucial to remember, though, this mode doesn't eliminate the WLC. It makes it even more central. And it's the opposite of local switching because the data does come back to the WLC. It's about simplifying the edge configuration. This really defines one aspect of FlexConnect switching modes.
So for large organizations trying to manage hundreds or thousands of locations, this approach can drastically streamline how they deploy and manage Wi-Fi. It reduces the configuration burden at each remote site, making the overall network easier to control and scale. Central control simplifies the distributed edge. All right, final scenario. Let's bring it back to quality service, QoS, one last time. An admin is configuring QoS, maybe for a critical video conferencing application again. Now, the network team has already done a good job marking the video traffic with the correct DSCP values on the wired part of the network. What specific thing must be configured on the wireless LAN controller, the WLC, to make sure those wired DSCP values are correctly translated or mapped into the equivalent wireless priority values, which are called user priority or UP?
This is a super important point for end-to-end quality. To make that translation happen seamlessly, you absolutely need to configure a wired-to-wireless QoS mapping policy on the WLC. Think of it like this. The wired network speaks DSCP for priority, but the wireless network, specifically the 802.11 standard, speaks user priority, or UP, values within the Wi-Fi frame headers. There are different languages for saying this traffic is important. The mapping policy on the WLC acts as the translator. It looks at the incoming DSCP value from the wired side and says, okay, this DSCP value corresponds to this UP value on the wireless side.
Got it. So it's like a translation table. Without that explicit mapping, what happens? Does the priority just get lost when the traffic hits the airwaves?
Pretty much, yes. If you don't configure that mapping, the WLC might just find a default, maybe lower UP value, or potentially no specific priority at all on the wireless link. So all that careful QoS marking done on the wired side could effectively evaporate once it goes wireless. Just enabling AVC or using a generic QoS profile like Platinum or Gold isn't enough. Those profiles use the UP values, but they don't perform the crucial mapping from wired DSCP to wireless UP. That mapping is a distinct configuration step. This is the core of wired to wireless QoS mapping.
So this is the invisible magic ensuring that your super important high-definition video call that was prioritized perfectly on the office LAN doesn't suddenly turn into a pixelated mess the moment your laptop switches over to Wi-Fi. It's about preserving that quality seamlessly for you, the end user, across the entire network path. #tag outro. So maybe a final thought for you listening. Next time you connect to a wireless network at work, at a coffee shop, anywhere, just take a second to think about those hidden layers. Consider the engineering and intelligence that's making sure your important apps run smoothly, or that your device gets the right kind of access securely, or maybe even helps a business find a crucial piece of equipment instantly. What other unseen systems, what other invisible intelligence is working tirelessly behind the scenes in your digital world every day? We'll be back with another deep dive soon. Thanks for joining us.